So if hopefully you've at least got on MyMathLab. If you haven't, please try to do that as soon as you can. Again, any issues that occur, the faster we can get it fixed, the better off you're going to be. So any issues, let me know. There's that 1-800 or 1-888 line in the syllabus. So just try to get everything up and running as soon as you can. I guess we haven't quite finished 6-1, but does anyone have any questions on the homework? I think we have 2 more examples left in 6.1. Yeah, 2. We might just briefly mention this. It's example 8's building off of what we've already done with position and velocity. Just another step removed. So we're actually given the acceleration, initial velocity, and initial position, and we want to find the velocity function and the position function. So remember, we had 2 ways to do this. There was the antiderivative method, where we could find the antiderivative and then use the initial conditions to find the constant, c. Or we could use the fundamental theorem of calculus method, which was here in this box. So if we look at it through that lens, it's the function equaling to the initial value of that function plus the integral, and then this v here, of course, is the derivative of s, right? So we could just make a similar statement with regard to velocity and say that v of t is the initial velocity plus the integral from 0 to t on this function's derivative, right? So v prime, a of x dx, and in the same way get the velocity function from acceleration. So hopefully that's not too far of a stretch. Right, let's see here, this is. And this is s prime of t, or s, I guess s prime, it's whatever. Did it again. Sorry. But that's kind of the pattern, and if there were other derivatives involved, we could successively find the other functions. So we could also use this method here to find both velocity and position in example, I think it was 8. Yeah, we did that one. So it was example 8. And it doesn't specify a particular strategy. So in that case, it would be up to you as to which one you wanted to use. So I don't know, if you want to work that and check to see if it's right, we're just going to skip that because we are a little bit behind. But it's almost identical to the ones we've done so far. Is that all right? And so this last example is going to illustrate more of a general change. So here at the bottom of the page with example 8 on it, we did briefly look at this table and said, here's position, velocity, acceleration type stuff, but more generally we can think of it as net change, future value, rate of change, etc. So those can all be applied to broader topics like population, for instance. So when records were first kept, t equals 0, so that's saying the initial population was 250 people. And during the following years, we're given this growth rate. So that's p prime of t is the population growth rate, not the population. Okay. So they want to know what is the population after 20 years, and the second part is to find the population at any time. Again, I guess there's a couple of ways to do this. We wouldn't necessarily have to start out with part A. The population after 20 years entails that we know the population function, and then we plug a t-value of 20 into that. So you could start off just by finding the population function, p of t, and then plug 20 in to answer A. So we could do B first and then A, or we could do A and then B. It doesn't really matter. Okay. But let's try to just fit this in with what we're doing. If we're trying to find the population function, P of 20, how would we construct that?
P of 20 is 250, or do you want P of the initial P of 0, or?
Okay. Yeah, either one. We have the initial value P of
Gotcha.
0.
Okay. Plus the integral of?
Plus the integral?
Yep. From 0 to 20 of 30 plus T, or,
You're right,
proper
right.
function.
Of P prime?
Yep.
31 plus T to the 1/2. Okay. Do you all agree with that? Yeah, so we're using that. I mean, and this is essentially like finding the position function given the velocity using the fundamental theorem of calculus method. Or if you go back a previous page, that is the future value function. So the quantity is the initial quantity plus the change of the sum of the change of that quantity. And remember, in this generic statement here, this t value, this t value here matches this upper limit of integration. So that's, since we want to know the population at 20, our upper limit of integration is 20. And of course, our initial was measured at 0, but if it's something different, it's going to match the lower bound there. So we just need to compute that. And you know, again, thinking ahead in part B, we have to find the population function, P of t. It doesn't specify how to do so. So we could say, all right, well, I'm given a derivative. I want to find the function, so let me find the antiderivative of p prime. That'll give me the population function plus c. And then I'll just need to figure out what c is. And that'll give me part B. At which point, then I can plug 20 into that. All right, so then we're going to have enough space here. Okay, so the antiderivative, let's just take this 30 out. T plus 3/2, or sorry, t to the 3/2 times 2/3. Oh, that's not good. Evaluated from 0 to 20. Okay. 250 plus 30. F of the antiderivative at the upper bound, 20 plus 2/3, 20 to the 3/2. And of course, the second one would be 0. All right, so you know, as we expect, this is going to output a number, and that number represents the population after 20 years. So should come out to be a 2,638.85.
Would you round up because it's people? Like, do you usually care about that?
I really don't care. I mean, in there, yeah, if we're measuring the number of people, then yeah, we would probably say, I don't know, probably say 2,638, because we wouldn't count that 0.85 person. Yeah. Does that make sense? Hopefully it's nothing too terribly off from what we're doing. And then the population of any time, does anyone have a preferred method? Would you rather do the antiderivative and then solve for C? Or do you prefer this method here? Does anybody have a preference? This one? Okay. So, there's a couple like this on your homework. It doesn't matter how you start. So I think, looking at it one way and then the other is helpful. But it's totally up to you and what makes sense, I guess. So capital P of T would be equal to what? How would we find it?
Do the integral of 30 times 1 plus square root of t.
Yeah. What is that? Where would we go from where to where?
Oh,
You could leave it
we just leave it,
indefinite.
yeah.
Just leave it. Okay, so this would be the antiderivative method then, right?
Yeah.
Because we're just going to find the antiderivative. This is going to give us the same antiderivative we had up there. And then from there we use the fact that P of 0 is equal to 250 to find C. Yeah, so that would be the antiderivative method. Use that to find C. So we'll call that number 1. The other method, P of T, with the fundamental theorem method, what would that look like?
You'd take 250, the initial value,
Okay.
and add the integral from 0 to t, and then you would take the function, you would put it to the variable s instead of t,
Okay.
just a dummy variable for notation purposes. So
All right.
31 plus s to the 1/2 ds,
Okay.
and then you would take the integral of that, and then you would replace the s with a t because you're doing a definite integral.
All right, good. Yep. So, feel free to use whatever variable here. The thing is you want this, since this is a function of t, you want this upper limit to be t. Whatever variable you use here, s, x, w, just make sure it's not a t. So we've got our initial value. Again, this is going to turn into a function of t. So our antiderivative, we had, this would be s. So very similar to what we had above. And then go ahead and distribute the 30 so we can get rid of the 2/3. I guess it really doesn't matter, but however you prefer. And then this is evaluated from 0 to t. Okay, remember the 0 to t, in this instance, since we've chose s, those are s values. So we got 250 plus this quantity, 30t. Plus 20 times t to the 3/2. The upper limit, minus all of that at the lower limit would just give us 0. So we'll just straighten that here. So there's our function of t. It's 250, 30t, and 20t to the 3/2. Same result you get by solving for c, etc. I guess we should leave that. So again, now that we have a population function for any t, we could go back and do part A, plug 20 in. And we could also do that now just to verify that they do coincide. That's the basic idea though. Do y'all have any questions on that? Okay. So, oh, and the last page is just a summary. So 6.2, we're not going to really do a lot in 6.2. It's you do have homework over it. I'm just curious, how many people took Calc 1 here? Okay. So if you took Calc 1 here, you really ended Calc 1 with this section, or should have. So we might do a couple of examples just to get an idea. I know I have like 7 or 8 examples. We're definitely not going to do all of them. And the idea is it's kind of a more generalization of the standard Riemann sums that or areas that you looked at. So remember, those were for the Riemann sums. When we initially looked at them, we had some function from A to B, and we wanted to know the area. So what we had to do was just cut this up into a bunch of little pieces, and then we looked at the areas of the individual rectangles. And so that's what's represented here when you see this. Think about this as the height and the width. So that's the area of the first rectangle. And we do plus the area of the next rectangle plus, right? But that only gave us a finite, even if we went to 1,000, we've got 1,000 rectangles, approximate area. So then we said, in order to get an exact area, we had to let the number of rectangles approach infinity. So that's the same as this limit. Delta x represents, let's just say that's one of our rectangles. Delta x is just the width of each rectangle. So if you put in infinitely many rectangles in there, then their width has to go to 0 eventually to get infinitely many of them. Okay. So that was fine for that particular situation. What we're going to extend that to is, what if we're not looking for the area that's bound between a function and the axis? What if we want the area between two functions? And that's what 6.2 is all about. So like if we had these two functions and we wanted to know what the area was, then again the same strategy is applied, that we're going to cut that region up, fill it up with a bunch of rectangles, compute the area of each rectangle, and then add all of that up. So, and this idea does extend into 6.3 and then 6.4. So here, when we said, what's the height of this rectangle? Well, it was just this distance from the function to the axis, right? So it was the distance f of x minus 0. So we just call that f of x because it was redundant to write. How do we measure the height of each one of these rectangles? Like, what would the height of that one be? The what?
F of x minus g of x.
Right, f of x minus g of x. So the height of that particular rectangle, you know, if you knew this y value was 10 and this y value was 5, it's the height of that rectangle is 5, right? You just take the top minus the bottom. So that's that idea might be easily overlooked in this type of situation, but I think it's more important in 6.3 and in 6.4 when we start looking at volumes to kind of get your bearings and compute volumes with a similar notion. Okay, so it's f of x minus g of x. For the height of each rectangle. More generally, when you're slicing things in a vertical direction, you know, here, since the thickness, if you will, of each slice is in the x direction, it told us a lot of information. It said, well, since I'm slicing it this way, we always ended up integrating those with respect to x. But in this situation as well, when we're integrating with respect to x, the height of each rectangle is also determined, just more simply by remembering it's the top minus the bottom. Same thing here, it's just the bottom function is 0. Top minus bottom function being y equals 0. So what do you think then the area looks like? The area of this region bound by those two curves would be what?
The integral from A to B
Integral from A to B?
of f of x minus g of x.
Dx. There's the height of each rectangle, and here's the width of each rectangle. So that integrand is the area of each rectangle. Remember, a definite integral is just an infinite sum. So we're summing all the areas of the rectangles that fill in that region. So that, you could look at this as the more generic Riemann sum. What we started off with was the very specific Riemann sum, where this function g of x was always 0. So, if we can look at it this way, we can tilt our heads 90 degrees and look at it another way. And it works exactly the same. So if we had this function, let's call it h of y, and this function that's w of y. It's called the intersection points here, C and D. It's the same idea. What is the area bound between those two curves? Let's fill this up with a bunch of rectangles now running this way. I'm going to keep in mind that we're going to exaggerate one of these rectangles. It has a thickness now in this direction, which is the y direction. So if we're going to look at it from this viewpoint, then we have to integrate with respect to y. So that means just like here, a and b were both x values. We're integrating with respect to x, two functions of x. If we're going to look at it this way, our bounds have to be y values. Our functions have to be in terms of y. Right? So it's the exact same concept, just rotated, if you will. Is all that somewhat clear? Do you have any questions? So, why would we have two ways to do that? Why does it matter? Why not just one? Like, why wouldn't we just integrate with respect to x all the time?
Because there's multiple values for y.
Okay.
There's multiple x values.
One might be easier than the other two.
Yeah. So, like, if you had multiple values, you mean you would have multiple integrals to compute?
Yeah.
Yeah. So certainly, one of these might be a little bit simpler to compute than the other. Yeah. That's pretty much the standard of why we have multiple ways to do things. Not only that, though, if you remember implicit differentiation, does anybody remember that? So, like, the reason we differentiated things implicitly was because why? Anybody remember?
It was really difficult to do it explicitly.
It's really difficult to do it explicitly, and yeah, sometimes it's even impossible to solve a function for y or for x. So we may not do this example, but I do want to point out this example number 3, for instance. We're given two functions of y, and they're cubic functions of y, right? So we could say x is y cubed minus 4y, and say I don't want to do that with respect to y because I'm just used to doing that with respect to x. You're going to have a whole lot of trouble solving that for y because you've got to solve a cubic equation, right? And those aren't easy to solve. So in a situation like this, we would say, well, it's clearly easier to do this with respect to y. The functions are already in terms of y, and even if they weren't, like, they're difficult to solve for. So, like, if that were just like x equals to y, that would be a pretty even trade-off as far as solving for x or y. So sometimes, it's not saying that this one's impossible to solve for y, but each one of these curves here, like this red curve, would represent, you would have 3 different functions of x representing that red curve. So it would be extremely difficult to integrate with respect to x. Okay, so we've got these 2 ways to look at it. Again, they're telling us the same thing. It's just the area bound between 2 curves. I'm going to skip that first example too. It's more straightforward. And yeah, I just want to mention this one here. Sometimes you have to split up your region. A lot of times the difficult part here is, looking again at the more generic situation, the difficult part here is figuring out what this A and B are. In other words, where do those 2 curves intersect? Because oftentimes that's not given to you. So if we need to find the region bound between 8 over x squared, that's red. 8x and x. Sometimes there's confusion as to, like, which region do I look at? It's the region bound by all 3 of those. So sometimes it's a little bit, sometimes it's totally obvious, sometimes it's not totally obvious. But the area we're finding is not this piece right here, for instance, because that piece is only bound by x and 8 over x squared. We want the area that's bound by all 3 of those. So we want to find this area here. Okay, cool. So kind of similar. That's the area we're finding. So notice it's really beneficial to draw these out, or to at least try to visualize these regions, especially in the next two sections. So if we're looking at this, thinking about filling this up with rectangles, I think that's the first step to finding area and volume for anything, is to just visualize which direction are the rectangles running, because that's going to dictate the rest of the problem. Since my rectangles are vertical, up and down, again, we'll exaggerate one of these, but it does have a thickness in the x direction. So this thickness right here is dx, which tells us that I need to integrate with respect to x. My bounds need to be in terms of x, and my functions need to be as f of x or g of x. Okay, so I think that's always important as a step one.
How do you know?
How do you know?
Can't you make it in terms of y as well?
You could do it in terms of y as well, yeah. So that's why I would recommend drawing a picture so you can keep your bearing. Like if I wanted to take this region, but have my rectangles run this way, then the thing I set up, my bounds are going to be in terms of y, the function is going to be in terms of y, or you know, so whichever one you're going with, stick with it. Here we could do either or. These functions are already in terms of x, so I'm just going to integrate with respect to x, so I don't have to solve for x. But we could certainly do it this way. When you find the intersection points, we need to look at the y coordinates, you know, so just be super mindful. But I think this is definitely the most important thing to establish first. And I think it's a little bit more evident as to why when we start looking at volumes. Okay, so we're going to stick with this one here. If you want to try it with respect to y, you should get the same area, right? It's the same area whether we look at it this way or this way. Okay. Any other questions about where we're at right now? So we see here though that, all right, we've got this intersection point where 8x intersects x. This intersection point where 8x intersects 8 over x squared, and this intersection point, right? I mean, from the graph, we might guess that that's 0. Right? That one's sort of trivial. So I guess there's a couple of things to do at this point. We've established kind of the setup. We want to find the points of intersection so we know where we're integrating from. But remember, when our slices, our rectangles, our elements, whatever you want to call those things, whenever they're running in the vertical direction, the height of those things are measured by what? By how? How do I measure this height?
Function minus the function.
The what?
The function minus the function.
Yeah,
Whichever function.
Which function? Bottom minus top?
The
Or top minus bottom? Top minus the bottom. So having this picture, we can see, all right, well, all of these rectangles here, the top minus the bottom, it's always 8x minus x, right? Until you hit this sort of transition point where now these rectangles are the top 8 over x squared minus x. So you see the top and the bottom, well, actually the bottom function here stays the same, but the top function is different depending on where we're at. So really, you've got to break this up into two different pieces. We're going to put this I think this is a dotted line. We're going to put this dotted line here because that's sort of the transition when the rectangles, how we define their height when it changes. Is everybody okay with that? Let's try this again. So we have this one, and then we have this one. That's making that area up. So we'll just draw one of our rectangles here. Okay. Yeah.
Can you not do the right function minus the left function and then minus the bottom function?
What do you mean, the right minus the left minus the bottom?
Mhm.
For what we're doing here?
Or does that not work at all?
No, because if we're doing right minus left, we're measuring something that direction, and those rectangles all have thicknesses in the y direction, if you will. So that would be a dy situation if we're doing right minus left. So again, we need to find these points of intersection, and we'll just highlight these. This point of intersection here, as far as the x value, is the same. That dotted line is the same. And then we have this one over here. So those are our points of intersection, which give us the upper and the lower limits of integration. All right. So this point of intersection here, we said looks like it's at the origin, but we can just verify. It's when 8x is equal to x. Or when 7x is equal to 0, or when x is equal to 0. Okay, so we know this x value is 0, and maybe we would have guessed that from the graph, but some of the examples, the graphs aren't provided, so you want to make sure that you're drawing a picture to sort of get your bearings. So that's got an x value of 0. The second point of intersection here, let me just do this for this one here. That point of intersection is when 8 over x squared equals 8x. So we'll multiply here by x squared. When x cubed equals to 8. X cubed equals 8 when x is 2. It's 2 and negative 2, but again, from the graph, clearly we're not intersecting at negative 2. So that's got an x value of 2.
Did you say when it is equal to 8x?
I think you did the other one.
Sorry, what?
That one you go over there,
This one?
for the intersection, isn't that the far right one you just did on that one?
Yeah, I think so. Yeah, when the red intersects the blue, when 8 over x is, so that one's an x value of 2, my bad. Yeah, so I'll just fix it this way. This one isn't 2. This one's our purple one. That color, I think. So that's an x value of 2. Yeah, thanks. And then, right, the blue one is where the green and red intersect. So let me go up here and label this. When 8x equals to 8 over x squared. Okay, so again, multiply both sides by x squared. So when x cubed equals 1, when x is 1. You know, and don't, you know, don't rely on the graph unless you can like look at this and say, all right, yeah, well, it looks like from the graph that it's 1. You know, you need to plug 1 into both of these to see that it's the same. Sometimes those things might be just a little bit off. It could be 1.02 or something like that. So, you know, you really want to make sure that they are intersecting where they appear to be intersecting. So that's our x value of 1 here. So is this one. This is x value. All right. So you've got 2 different integrals to compute to calculate that area. Yeah, we'll go ahead and put it down here. But notice to find this area, x is ranging from 0 to 1, and it's always the top minus the bottom, which never changes, 8x minus x. Okay, that's for the first piece, plus the area of the second piece. And that was 8 over x squared minus x. Is everybody all right with that? Any questions? I'm just going to draw this here. All right. So we could just call that first one 7x. How do we integrate 8 over x squared?
Make it 8 x to the -2.
Right, we just turn it into a power. So this is 8x to the -2 minus x dx. Okay, and that's our setup. I think I'll just stop there. Everything else is just a power rule, so it should be straightforward. Let's see. Yeah, if you're going to work that, you should get it to come out to be 6. Do y'all have any questions on that example? All right. So this one here we mentioned earlier in terms of y. You just highlight these 2 functions. This function here on the, I guess on the left, the red one is the y cubed minus 4y. And whatever this color is. That's the y cubed plus y squared plus 8. Bound, so we've got those 2 curves, and it says for y in between -2 and +2. So you probably can't see it very well. There's y equals to 2, -2 rather, and here's y equals to 2. So again, when it says find the area between these graphs for this particular y value, you know, in effect, what that y value does from -2 to 2 just gives us sort of the top and the bottom of that region, but it's the area that's shared by all of that stuff, right? So we're really finding all of this area. And we'll just set this up, but just be mindful now that our cross sections, our slices, are now running vertically, which means these rectangles have a thickness in the y direction. So we need everything in terms of y. So the area is the integral. Anybody want to take a stab at it?
Right minus left.
The right minus the left, yeah. So what are the bounds of our integral? -2 to +2, right? It's a y value of -2, a y value of +2. Right. And again, the bounds of integration are determined by wherever you're filling your rectangle. So we start with this rectangle here, and we end with this rectangle up here. Is everybody able to get that? All right. And then what function are we integrating?
Function of hy minus gy.
Right, h minus g. In other words, the right minus the left. Be careful, since we've got to subtract off the function on the left, and the function involves more than one term. Make sure you're subtracting off the whole thing. Okay, so that's the setup. Again, you're just integrating powers of y. Everybody okay with the setup? Are there any questions? Okay. It's 112 over 3. So if you're not, if you know, any of these setups and you have questions on, please ask, because what we're going to do in the next section is we're going to take something like that and revolve it around an axis to create a solid, and we're going to calculate the volume of the solid. So it's calculating volume entails us to only focus on area, and so this idea of how we're calculating this area is perfectly relevant to the volumes that we calculate. All right, let's go to, so let's look at example 4, and then we'll look at example 7. So find the area of the region bound by natural log of x, y equals 2, y equals to 0, and x equals to 0 by setting up an integral with respect to y. So here they do tell us integrate with respect to y. And we'll see why in a minute. So no graph provided. Hopefully you remember the natural log graph. It's super common. So what does the natural log graph look like? It goes this way relative to the board?
Yeah.
Yeah.
It starts with the right, goes to the left, and then down.
So
Okay.
start at x equals 1.
Right?
Like that? Do y'all agree? Is that the natural log? What is this point here?
1, 0.
1, 0. Yep. So the natural log function, y equals to 2. It's right here. Y equals to 0, right here. And x equals to 0 is right here. So we're finding the area of this region. So notice it tells us to integrate with respect to y. So which direction are the cross sections running? Vertical or horizontal?
Horizontal.
Vertical. Horizontal. Vertical, so remember if they're running vertical, right, then they have a thickness in the x direction. Right? So that would be perfectly fine if we needed to integrate this with respect to x. It says with respect to y, so we need our rectangles to run this way. So they have a thickness dy. Is everybody okay with that? Makes sense? Okay, so then what would the area of this region look like? Anybody want to take a shot?
So you raise both sides to e, so you get e to the y equals x. So take the integral from 0 to 2.
0 to 2?
Of e to the y dy.
All right. Let's look at that for a minute. What do y'all think? So we can look at the bounds. If we're going to integrate with respect to y, as we're told, this y value here, of course, is 0. And we're going to fill the region up with rectangles that stop at that y value there, which is a y value of 2. Okay, so we've got 0 to 2. Makes sense. Why e to the y and not ln of x?
It's harder to, I guess, calculate with ln to the x versus e to the y.
Yeah, right. One, how do you take the integral of the natural log of x? What function's derivative is the natural log of x? Right. Yeah. So how do you know that?
Integration by parts.
Integration by parts, which we haven't talked about. So that's kind of off the table. The other reason, and the main reason, is because it says with respect to y. So this needs to be a function of y, not a function of x. If we were integrating with respect to x, then natural log of x as it is perfectly fine. So since we want to integrate with respect to y, this function needs to be in terms of y. Or solve for x. Okay, so if y is the natural log of x, e to the y is equal to x. So that function of y, which is x, that function of y goes here. Does that make sense? So you're going to have a real hard time if you say, all right, well, with respect to y, my bounds are from 0 to 2, which is y, and then you try to integrate ln of x dx. First of all, you're integrating with respect to the wrong variable. You can't integrate ln of x yet, and 0 and 2 aren't x values, they're y values. So, there is potential to mix up some stuff here. I just keep harping on the volume stuff because it is very, very parallel to what we're doing here. But if you have to find the volume using a certain method and you don't know how to set that method up, you're going to use a different method, which may give you the same volume, but you're going to end up losing points because you didn't do the correct method. And most of the time when people do the incorrect method, the setup is incorrect too. So just want to make sure that we're, all of our bearings are straight before we start tackling any of that stuff. Any questions on this?
For
What's-
the result,
Yeah.
do you want an actual decimal number, or can we leave it as like e squared minus 1?
Yeah, I would leave it as exact. The antiderivative is e to the y, so yeah, we get e squared minus 1. So that's exact. That's fine. All right, any questions on that? Honestly, if you're in physics, you're probably drawing pictures. at least some diagrams to solve some of your problems. No shame in drawing diagrams here either. I would definitely recommend it. If you're not given a graph and you have to find these areas and these volumes, the first thing you should do is draw the graph. Okay, we're going to look at example 7. It says use the most efficient method to set up the appropriate integral to find the area between the curve. So it's just a, we'll just set this up. And we'll say to find the area between the curves of sine x, sine of 2x on the interval from 0 to pi. Because this is pi here. All right. Yeah, that's okay. So we've got these two curves here, which I don't know if you can see that faintly. This looks red to me. And then we'll do this other one in blue. Okay. So which one's which? Which one's the sine of x?
The red.
The red? Does everyone agree? Red is sine, blue is sine 2x. Yeah. Okay. So let's try to establish the intersections, and then we'll take a break. We have a little bit of thought required to find where these intersect. Again, maybe this point here is trivial, and this point here is trivial. We know that the interval is from 0 to pi, but we need to find this point of intersection too. So we've got two options, right? We could integrate this with respect to x, which means my rectangles would be running in this direction. If I integrate it with respect to x, again, the height of each rectangle, top minus the bottom, that changes as we pass over that point. So we're going to have two different integrals describing this area. If we do this with respect to y, would that be easier? I mean, you can see even right there, that's kind of a problem, right? If we did integrate this with respect to y, then I have to say this function here is solve for x. So x is sine inverse of y. Do we want to integrate that? Probably not. So I mean, that would be enough to just stop and say, well, I don't want to integrate inverse sine, I'd rather integrate sine. It's in terms of x already, so let's do dx and not dy. So we're going to do this. Most efficient method with respect to x. Okay. So the endpoints, they're fine. This intersection point, when does the sine of 2x equal to the sine of x? How do we solve that equation?
So sine x, use a trinity. So you be sine x, sine 2x would equal 2 cosine x, sine x.
Right. Right. So you got to remember the identity for sine of 2x. This identity is really common for us. So this sine of 2x we're going to write as 2 sine times cosine. And why are we doing that?
Because you're trying to find a point of intersection between sine x, the first point of intersection.
You can cancel out the sin x.
Oh.
Yeah, well, not necessarily. You can't cancel out the sine x. I mean, I guess you can. We can divide through by sine of x if what? If sine of x is
Oh,
not 0, right? We can't divide by 0. If the sine of x is 0, we can't divide both sides of the equation by sine x. We see here sine of x is 0, right? But the reason we're writing it this way is because now we have basically two terms, this term and this term, both of them involve sine. So we're just going to get both of those terms on the same side and factor that sine out. Minus sine x is equal to 0. And so we factor that out. So I mean, yeah, if you divide both sides of this equation by sine, you do get the equation 2 cosine x equals to 1, but you would totally miss out on when sine is equal to 0. For this particular equation, it's not that important because we do have the graph with the endpoints 0 and pi, but leaving out the x values when sine is equal to 0, it's just not good, right? You're leaving off half the problem. Even though leaving it off here is not that big of a deal. But you never want to divide through by a function of x when that function of x can be 0. So instead you want to factor it out, if possible. Okay, so 1 when this is 0, when sine is 0, and when 2 cosine x minus 1 is 0. We know sine of 0, or sine of x rather, is 0 when x is 0, pi, and so forth. But again, we're not concerned with any of these values after pi, because that's outside of our interval. Okay. This one, we've got another 0 here when cosine of x is 1/2. So cosine is 1/2 when x is what? Pi over 3. And the next one's outside of the interval from 0 to pi, right? It's 5 pi over 3. So again, we're not concerned with these out here. So those are our points of intersection at 0, at pi, and at pi over 3. So now we know that point in the middle here happens at pi over 3. Yeah, question?
So can we think about a scene like 2x equal to the sin x, and we can do like the 2x equal to x. That means x only we have 0.
Mm-hmm. Right.
And after that we can like divide sin x to the both side.
So you just sine? You couldn't divide just sine.
No, I mean if the sin 2x equal to sin x, and we have like the one is the x equal to 0 at that point, and after that we can like divide two sides of the sin x, and we don't miss any like x by 0. You know what I mean?
Well, kind of. If we know like when the sine of 2x is equal to sine of x, when 2x is equal to x gives us that value of 0.
Yes, and we don't miss that point.
Right. So, but wouldn't we miss this one here because that's also when it's 0, or also when they're equal, right? Wouldn't we miss that pi? Yeah. So you've got to be careful with trig functions. They're a little bit, I think the frustrating thing with trig functions is there's so many identities for them, right? And when you look at solving an equation, it's not always intuitive, like, what should I even do? And 2, if I'm going to use an identity, which one of the 35 identities is going to help me out, right? So I will say that, when you have a situation like this, you want the same trig functions on both sides so you can factor that out. There's more than two terms like this, then typically it's that situation where it might be some sort of quadratic type of thing. But again, they're all kind of unique. The things you did in pre-calc to prove identities and stuff, I promise the things here in Calc 2 don't really get that involved. It's really just if you can remember basic stuff, you'll be all right. Okay. So does anyone have any questions on this? Then after break, we'll set up the integral. Any questions on that at all? Okay, we'll take 10 minutes. Section. Like I said, typically the points of intersection are usually the most difficult part unless you have to split it up into a couple of different integrals. So then our area would be we have the first region bound by 0 and pi over 3. And again, in here we want the top function minus the bottom function since our rectangles are running vertically. Top minus bottom, dx, plus the area from pi over 3 to pi. Again, top minus bottom. Okay, so what do we label these as? So 2 sine minus sine. This one. And then the other way around here. Okay, so that's our setup. So that we were just asked to set it up, so I didn't actually compute this. Excuse me. Okay, any questions on that?
Are there specific instances where you'd want us to write out the format for sine 2x, or would it be fine to leave it like that?
Yeah, like, what do you mean? As far as like integrating it,
Or like the 2 sine x, cosine x, would you prefer us to write that out or leave it sine 2x?
Okay, so it really, that depends on what you're doing. So as for like solving the equation, yeah, we wanted to write that out as 2 sine cosine. But if we have to integrate this, which we know is the same as this, well, I mean, okay, which one looks more appropriate to find the antiderivative of? The first one? All right, can we find the antiderivative of this one?
Not yet, at least.
Maybe not yet, at least, but what else?
Like
Can we try?
substitution maybe?
Right. The only other technique we would have is a U substitution. So if we did write it like this, depending on the identity and the trig functions involved, you may or may not be able to integrate a product because we haven't technically talked about how to integrate a product of two functions of x. But if you did write this one here, hopefully you're at the point where you don't have to do a U substitution for this one. But if you are, then that's fine. It's just going to be, you're going to be a lot less efficient with a lot of things we do. So it's easier just to know that the antiderivative of that. Okay, so what could we possibly try as a U substitution here?
T equal to the sin x.
Okay, so sin x is equal to what? Say that first part.
The t.
Okay, so t or u. Okay, so dt is cosine x dx. Right, so this part is now our new differential, and this is just 2u. We can certainly integrate 2u. So yeah, either way here is fine. But sometimes, like I said, you got to be careful as to, it depends on what you're doing. If we were like trying to integrate some other trig function that we wrote as an identity, one we might be able to do pretty easily, the other one might not be able to do. Yeah. Okay. Any other questions? Okay, so there's that summary here, and then I'll go ahead and add another page for a couple of things in the homework to remember. So for 6.2 homework, one of them we've used quite common already. The other one was for cosine of 2x. Does anybody remember the identity for cosine 2x?
Oh, it's just square x minus square x.
Yeah. Cosine squared minus sine squared. And remember for cosine of 2x, there was actually 3 different identities, all based off of this one right here. So if you remember this one, the Pythagorean identities, and I guess, you know, backing up even further, if you remember that the sine of 2x is the sine of x plus x, and you remember that identity for sine, then that's where this identity comes from. Because you just get sine of x, cosine of x, plus sine of x, cosine of x. You've got 2 of those, right? Same thing with cosine of 2x. Cosine of 2x comes from the sum identity for, or sum and difference, but sum here for cosine. But if you can remember these, rather, specifically this one for cosine and the Pythagorean identities, sine squared plus cosine squared is equal to 1, and the other 2 identities for cosine of 2x come through. So the other versions of them, 2 cosine squared minus 1, and 1 minus 2 sine squared. Again, it would, you know, which one you work with depends on what else is present in the problem you're trying to solve. Like if there's a cosine squared and a cosine, then that's a quadratic type of equation you're solving. So you'd probably want to write cosine of 2x as this one here in the middle. If there's a sine squared and a sine present, then that's again a quadratic. So it just really depends on what else is present in the equation you're trying to solve. Let's see what else. Yeah, the integrals for cosine squared and sine squared. So integrating these is quite common, and to integrate those, we rewrite those in terms of their identity. 1/2 cosine squared x is 1/2 times 1 plus cosine of 2x. Sine squared 1/2 times 1 minus cosine of 2x. Yep. So those probably worthwhile remembering for this section's homework and going forward in general. Everyone okay? Any questions? We're going to move on to 6.3. So the next 2 sections deal with volumes. The general slicing method and the disk and washer method is in 6.3. Yeah, 6.3. And then the shell method is in 6.4. So just as a reminder, when we find an area, what we did was we filled this region up with rectangles, and we computed the area of each rectangle and added that up, right? So that when we see this, that's the sum of each rectangle's height times each rectangle's thickness. And height times the thickness is an area. So we're just adding up a bunch of areas. So when we're talking about now here finding a volume, we're going to look at a couple of like geometric figures just to kind of get the sense of how that notion is going to be extended. And then look at more like exotic regions here. So this prism, really the key is the consistency of the figure throughout, right? Like if we imagine cutting this prism or this cylinder or this prism, like no matter where you cut it, as long as your cuts are consistent and you're not cutting one at an angle, one horizontal or whatever, then they're going to generate the same cross-section. Right? If I slice into this prism this way, they're all going to be these right triangles. So the way we can look at the volume of this thing is we can say that, let's just consider this a thickness. We'll call it T for thickness. And we'll calculate the area of the face and then multiply it by its thickness to get the volume. So we know this area is 1/2 its base times its height. So then the volume of this region is just that, 1/2 the base times the height times the thickness. Same thing here. If we were to slice this way, let's say horizontally, all of our cross sections would be circles. So we find the area of that cross section, and then we multiply by its thickness. So our volume is pi r squared times t. And cross sections here are all rectangles. Let's call that length and width, and this again thickness. Is everybody okay with that notion? That's the notion that does apply to these volumes that we calculate. So the first thing we're going to look at is this general slicing method that then sort of parlays into the Diskin-Marsher method and then the shell method in the next section. So like if you had to find the volume of a loaf of bread, you know, each cross section is pretty much uniform. I mean, you know, those weird little crusty end pieces are always kind of funky, but we have the cross section, we slice that up into a bunch of different cross sections of the same shape, if you will. We say, all right, well, what's the area of this cross section times its thickness? We've got uniform thickness for each piece of bread. We just need to know the area of the face times the thickness of this piece, the area times the face of the second, the third, the fourth, the fifth, and just add all of those volumes up. So that's what the general slicing method refers to. I think it's presented here on the next page. So you know, some sort of the volume of this gold figure here. We're still going to slice this up into a bunch of different regions, but instead of like in this setting where we're finding an area, we just found a length times the width. For the volume, we want to look at an area times the thickness. So we're gonna slice this region up, and notice that all the areas would be sort of this parabolic shape. So we would say the area of each cross section is a parabola times its thickness, and the more of those things we insert, or the more cross sections we perform, the more accurate that is. So once again, we're letting the number of those things go to infinity, which involves an infinite sum which again, an infinite sum is what an integral is, a definite integral is. Okay, so the key to finding these volumes here is we're gonna integrate the function a of x, where that a of x is the area of the cross sections. What does it say? Doesn't really say. Oh yeah. So the cross-sectional areas is that function that we integrate. The differential dx here is now playing the role of thickness, as over here with area it was just playing kind of the same role, but it was a one-dimensional thing. So we have, does everybody see the parallels here? This is an area, length times width. This is a volume, area times thickness. Okay. So when we're given a figure like this, we're going to say the first thing we really need to, the only thing we really need to identify that requires effort is what is the area of the cross-section. So if we're finding an area like we were in 6.2, we would just say, well, what's the height? It's the top minus the bottom. Here it's a little bit more effort because we have to find the area. So this example we're going to look at, it says use the slicing method to find the volume of the solid with a circular base of radius 5. So here's our circular base. And it says whose cross-sections that are perpendicular to the base and parallel to the x-axis are equilateral triangles. This is kind of... So we've got this circular base with this cross-sectional equilateral triangle. And you know, depending on where we are, we've got to imagine filling that entire region up with all of these equilateral triangles. And when we do that, we generate this figure here. So we're finding the volume of this thing right here. So I mean, yeah, the figure looks complicated, but fortunately for us, every cross-section is the same, just like in those prisms and then in that cylinder. So we can use this particular method to determine the volume, which entails all we need to do is determine what's the area function. And again, the area function is attributed to the cross-sections. Okay. So we know that the cross-sections are equilateral triangles. And the area of an equilateral triangle is just the 1/2 times its base times its height. But of course, that's not a function of x or y. So now the problem is, or the trick is, we've got to rewrite b and h in terms of x or y, depending on what variable we're integrating with respect to. So the way this problem is set up for us, what are we integrating with respect to, x or y? So it's kind of skewed here, right?
So with respect to y,
Okay. Right. So it says the cross sections are perpendicular to the base and they're parallel to the x-axis. So here's our x-axis. Our cross sections are running in that direction. So there's one cross section. The apex of that triangle, of course, is coming out at you. So dx dy. dy, right? That's a rectangle, right? It's like this thing here. Its thickness is in the y direction, so that's dy. I mean, we can exaggerate this if we need to, but So we have to have our bounds and our functions in terms of y. Is everyone clear on that? Okay. So we know the cross-sectional areas are 1/2 base times height. So I'm just going to rewrite it here. For this, we need B and H. In terms of y. So remember, this thing right here is the base of your equilateral triangle. So the length from here to here, or the length from here to here, is the length of the equilateral triangles. So the base in terms of y is defined how?
I'm thinking 2 square root of x 25 minus, or sorry, 2 times the square root of 25 minus x squared.
Yeah.
Give us the base.
Right. And how are we getting that? Well, I'm measuring something that's running in this direction. If this were an area, we would say that in order to measure that height, I just do the right function minus the left function, correct? So it's the same thing. Nothing's changed here. How long is this green line? How long is that green line? It's this boundary minus this boundary, the right minus the left. That will always be the case when your slices run horizontally. Okay, so what is the right minus the left? Well, it's dependent upon the equation of that boundary of that circle, right? So the equation of our circle, we're told that the circle has a radius of 5. So the equation of this circle is x squared plus y squared equals to 25. But remember, we want everything in terms of y. So we want to rewrite the equation of our circle in terms of y. In other words, we want that circle to be x equals 2. So we'll just write it here. Our circle we'll just solve for x. So this is, remember, we've got two representations for x. The positive x, of course, is this piece over here. And the negative x over here. Does that make sense? Anybody have any questions? And so then we put our rectangle here again. Now we know exactly what the right minus the left is in terms of y, because it's with respect to y. So there's the right minus the left. Sorry, that's a negative as well. So minus the minus root gives us 2 of those. So that's b. That's what b is equal to in this particular setting. questions? So let me just highlight this again. This is what we're looking at here. Again, just looking at that figure, we saw that those things, of course, those things vary as we move throughout. Right? So that triangle has much different base length than this triangle, has a much different base length than that triangle, and so forth. Is everybody good with that? Okay, that's B in terms of y. Now we need h in terms of y. And we're finding the area of the cross section, so it is the height of each cross section. It's the height of this triangle. So that's what we've got to measure that in terms of, hopefully in terms of y, if we have any hope of integrating this to find the volume. Any ideas here? Yeah.
Can we make a relationship between H and B rather than H and Y?
Yeah.
So we could draw an equilateral triangle. And we're gonna have define for the height based on this.
You're right. And why would we want to do that?
Because we know we already defined B X and Y, so if we define H and B, just
Right. Was everyone able to hear that? We've already defined the base in terms of y. If we can relate h to b, we've got b in terms of y, and we've related h to b, which means we can relate h to y as well. And it like in this two-dimensional setting, hopefully it's pretty obvious that this thing coming out at us, there's no way to measure that in the xy coordinate system, right? We need an xy and a z coordinate system to measure that. So our only hope is to relate this h back to this b, which relates it back to y. So fortunately for any equilateral triangle, there is always a specific relationship between the base and the height of an equilateral triangle. So there's our h. There's our B. And all we need to do is, as was mentioned, what was your name? Ryan. What Ryan was saying was we just can look at this, can cut it in half. This is still H. This is what? What is this length here? B, because it's an equilateral triangle. What is this length here? Yeah, half of B. We cut it in half. So we've got this right triangle now that we can use the Pythagorean theorem to relate H and B. So from this, use the Pythagorean theorem. Solve for H, or solve for B, whichever one. And then what you'll get is the relationship that's true for any equilateral triangle. You can always relate the base and the height. Anybody get it yet? this is h squared, we solve for h squared. So for any equilateral triangle, the height of it is always root 3 over 2 times its base. Okay, that's good for us because we already know what b is in terms of y. We just found that. B in terms of y is there, 2 root 25 minus y squared. Okay, so that turns into just the root 3 times the other root. All right, so we've got the base, we've got the height, we now know the area of the cross sections in terms of y. Does anyone have any questions? These are rather involved. When we look at the other volumes with the two methods mentioned, Shell and Marsher, Shell and Marsher method, they're a little bit more straightforward. Because it's kind of like the formula is always the same. Here with these general regions, it depends on the boundary and the cross sections. So usually these problems are a whole lot more involved than the rest of 6.3 and 6.4. But if everyone's okay, then we'll go ahead and continue because we're pretty much done. You've got the area. In terms of y, because we had dy from the very beginning, is 1/2 the base times the height. So then we'll just clean that up slightly. That's gone. We've got root 3. Times 25 minus y squared. So that's the area function. We need to integrate that function. Volume is the integral or the sum of the area times the thickness. Okay, does that make sense? Questions?
How did you get to that messy thing to that?
From here to here, you mean?
Yeah.
So the 1/2 and the 2 are gone. This root times this root is this thing squared.
Okay.
So it takes away that square root. So yeah, it's good for us because it's a lot easier to integrate now too. What are the bounds? Okay, let's see if anybody has those. Yeah.
Would it be negative y to y or negative x to x?
So we're integrating with respect to.
Oh, y.
Okay, so from negative.
Negative.
Yeah, the negative y to y, right?
Yeah.
But.
Would it be the negative 5? The 5 centimeters is 5.
Right. Remember the figure we're working with is here. The radius of this circle is 5. And that's negative 5, right? All of our rectangles are running this way, so we're going to fill it up from here all the way up to there. so we can get the volume of this whole thing. So from -5 to +5. Does that make sense? Those are the limits of integration for this here. We can make things a little bit easier using symmetry and go from 0 to +5 if we multiply the whole thing by 2. So it's totally up to you. It's just, if you're evaluating these things by hand especially, it's always easier to plug 0 in than it would be to plug -5 in.
Can you also pull out the √3?
Right, yeah, that's what I would do. The √3 is a constant, so I would just pull that out front and integrate this. So, I mean, it doesn't look terrible after we're finally finished with it, but it was quite involved. Maybe, I don't know, I guess it's relative. But I think it was pretty involved to find the area function itself. And once we've done that, it's pretty straightforward. All right, yeah, that should be 500 times √3 over 3 is an exact answer. That's our volume. Did it again. Do y'all have any questions on that? All right, we'll look at one more of those. We're gonna look at, I guess, deriving the area of a sphere. So we're going to derive the formula for the volume of a sphere with a radius of capital R, and we want our slices to be parallel to the y-axis. So since since with this method we're only summing up an area times the thickness, you never want to think about necessarily the full volume or working with the figure that is represented by a volume. We always want to translate that one level, one dimension down and work with that. So if I slice parallel to the y-axis, what are those cross sections going to be? Yeah, they're all circles. So let's just draw this over here. I'm not really dealing with a sphere. The boundary of the sphere is this thing right here, and the cross sections that we generate are, again, circles themselves here. So if I slice through the sphere, that's giving me this circle. We just want to look at it in this two-dimensional setting, because we're not concerned with the volume. In order to find the volume, we just sum up the area times the thickness. So we're concerned with finding the area of these things, not the cross section specifically. So cross sections. Are circles whose area is pi r squared. And let's label this, the greater boundary here is coming from the sphere itself. So this is capital R, R, negative R, negative R. So we've identified not only how we're slicing this vertically, which means we're integrating with respect to what? To x. Okay, so let's write that down. Everything needs to be in terms of x. And we've established that the areas, rather the cross-sectional areas are all circles. Pi r squared. So what do we need from pi r squared? What do we need to do? We can't just leave it as pi r squared.
You have to find a way to calculate r in terms of x, or lowercase r in terms of x and capital R.
Right. So just like in that last one, we said, hey, the area is half base times height. B and h had to be in terms of y. Here, r needs to be in terms of x, because we're integrating with respect to x. So let's just write that down. We need... And notice I'm using a lowercase r here because these things vary, right? If I'm slicing right down the middle of that thing, then then that circle, then this circle right here does have a radius of capital R, but only at that particular location. Anywhere else I slice it, it's going to have a different radius. So like this slice here just gives me this radius. This is the radius of that circle. So you just want to label it as a different R because it's not the same as the radius for the boundary of the sphere. Okay, and we need R in terms of x because of this dx, because of our slices. So just keep in mind once again that R is simply the distance from here to here, right? For any one of those circles that we slice. If it's this circle, the radius of that circle is just this distance from here to here, right? So how do we measure that distance from there to there?
Right, 2.4.
Do what?
Using the 2 points, 2 endpoints.
Yeah, and so this endpoint would be what? It's here on the x-axis. So just in general, how do you measure that length? What? Top minus bottom, right? So we can say that the radius of this circle, the radius of this circle is what? Do we really need to do top minus bottom? Do we really need to do top minus the bottom? Because the top minus the bottom isn't the actual radius of the circle, it's the diameter of the circle.
So it'd be 2 pi r squared.
Right, that's the
Top
circumference.
minus 0.
Well, 2 pi r squared, I'm not sure what that is. 2 pi r is the circumference. Half?
Half of top.
Yeah, half. The radius is only the distance from the top of the bounding function, which in our case is just this circle, minus the x-axis, which is 0. Or we could say, I'm going to take this whole length here, which would be top function minus bottom function, and then I have to divide that in half because I want the radius, not the diameter. Okay, so however you want to look at that, we can say it's R is half of the top minus the bottom, or it's the same thing as the top minus 0. However you want to look at that, we just need to measure half of it. Okay, so here again, when we say top, we mean from this figure here. We know that this figure is represented as a circle centered at 0, 0. whose radius is capital R. And so before we take the top minus the bottom, we're going to remember that our slices were this way, and we want everything in terms of x. So we want to solve this thing for y, so everything's in terms of x. Plus minus again. Sorry, this is x squared plus y squared equals to r squared. That is solving for y. Plus minus the square root of r squared minus x squared. Is everybody okay with that? That's the equation of that circle, which represents the boundary of the sphere, however you're looking at it. Any questions? Okay, so we've got a y that's positive and a y that's negative. So here's our y that's positive, and here's the y that's negative. But also our axis runs here, right? We're just measuring the radius of each one of these circles. We just need to do the top function minus 0. So the radius r, little r, is just the square root of r squared minus x squared. Is this 0? I don't know if that's necessary at this point. It's just this right here. That's our r. All right. So if this is confusing, please email me. Please ask. The way we're reasoning through this is how you're going to reason through every one of these types of problems. So we've got the radius in terms of x. Then that means the area function we can write out now. Thus, the area function in terms of x is pi times the radius, small radius squared. Which, of course, just gives us the pi times r squared minus x squared. So then we're finding the volume of a sphere, radius capital R. What is that going to look like? Volume is equal to
R squared negative R of R.
the integral from negative capital or lowercase? Negative capital R to capital R.
The area.
The area. Dx, right? I know some people are sloppy with their differentials because, like, in your head you know what you're doing, but please write them. It's going to be a lot more evident when we start doing like trig substitutions, and it'll be a lot more pertinent when you're in Calc 3. So if you're not in the habit of writing those differentials there, you're going to need to get into that habit. Okay, negative R to R, capital R, negative R. Negative capital R to positive R, capital R. Does that make sense? Where we're going, we're filling this region up with these rectangles. So we have our slices that are running this way, right? So the cross sections all run from here to here. Negative r to r. We're integrating with respect to x just because we were told to slice this way, right? So if you need to label these, those are both x values. Okay, the pi is constant, we'll pull that out. What's the antiderivative of r squared with respect to x? Sorry, someone over here?
XR squared.
X times r squared, y'all agree? What is r squared with respect to x? Is it a function of x? Clearly not. R squared with respect to x is a constant,
I was
right?
gonna ask if we could pull it out to the front because it's a constant.
Yeah, you could pull that out, but you need to have two integrals here. You'd have the integral of pi r squared dx minus pi times the integral from negative r to r of x dx. Sorry, x squared. Yeah, so r squared is just a constant, so we just tack on the x, and we have the antiderivative of x squared. We're evaluating that from an x value of negative r to an x value of positive r. And pi times all of that. So everywhere we've got an x, we're going to plug in a capital R, and then subtract off all of that with a lowercase r. So first one, you've got an r squared times this r up here for the upper limit of integration minus r cubed over 3. Okay, so that's the upper limit, capital R in for x, our antiderivative, minus. Now honestly, we could have made this a little bit easier too by using symmetry, right? Instead of going from negative r to r, we could have just doubled this and gone from 0 to r. But here we are, so we'll just keep going. Negative r now in for x. We have r squared times negative r minus negative r cubed over 3. And pi times all of this stuff, of course. So, just for time's sake, just work on simplifying, combining like terms. You do get 4/3 pi capital R cubed. Is that the volume of a sphere? 4/3 pi R cubed. Okay, so look over these. If you have any questions, email me, or we can start next class by answering some of these things. But make sure you understand this as we move forward, especially. All right then. See y'all. Have a good weekend.